Section 3.5 talks about the cross product. Suppose you have two vectors, v1 and v2, and these two are in R3. You want to take the cross product of the two. Now they have a formula for us, but we're going to really cut to the chase. We're not going to work this way. This is how we're going to do this. If we want to find u cross v, we're going to use a later theorem that says I, j, k. List the first vector. List the second vector. And remember, the I component, you cross its row and column, you get u2 v3 minus v2 u3. For the j, you multiply it by a negative, cross its row and column, you get u1 v3 minus v1 u3. And for the j component, cross its row and column, you get u1 v2 minus v1 u2. And again, I'm just showing you this because they might refer to that. Again, take the determinant of those, you get exactly what we got. The minus comes from the cofactors, and they talk about that later on. No, not in this section. That's okay, but that's how we're going to do it. Now these are some properties. Again, you're not responsible to memorize those, but just know that if you take u cross v and you dot u with it, well, let me show you how this works. If you take vector u, vector v, and cross the two, you'll get a vector that's perpendicular to both. The diagram's right there. There is the right-hand rule. If you line up your fingers with u and you curl your fingers toward v, the thumb will be the direction of the cross product, assuming that's between 0 and 180 degrees. Again, if we're going to verify these properties, I will provide. That's not a problem. It turns out, if you take the magnitude of u cross v, that's the magnitude of u magnitude of v times the cosine of theta, assuming theta is between 0 and pi. Now, there are a couple of important things about the cross product. If u and v are vectors in R3, so let's say u looks like that, v looks like that. If I take the cross product of the two, I'll get a vector that's perpendicular to both. We just mentioned that. And not only that, the magnitude of that will equal to the area of the parallelogram that engulf. So if you ever wanted to find the area between those, you just take half of the parallelogram or half the magnitude of the cross product. Now, this is important to know. If vector u, v, and w are all in R3, if they have the same initial point, that's very important. So they all share the same u, v cross w. So let's say that's that. Then if you dot those, you should get a 0. Well, this is how you dot them. You could take the cross product and dot it with u, or you could simply lift u right there, v and w, and find the determinant of that, and that should be 0. Okay, well, here are three vectors. They want us to find u cross v, so this is how we're going to do it. I, j, k, u first, that is 3 to negative 1, and v after 0 to negative 3. It's going to always be plus minus plus. We're going to always pick row 1, so the I component of the cross product would be cross its row and column. It'll be negative 6 minus a negative 2 plus 2. The j will always pick a negative, negative 9 minus 0. and the k component would be a 6 minus 0. Or I could simply say it is -4, -10, and 6. If you dot this with either of those two vectors, you'll get a 0. Again, I like to write this with components. Find u cross v plus w. Well, you could do v plus w first. V plus w is pretty much 2, 8, 4. Yeah, just add the components. And now if I take the cross product with u, that is I, j, k, in that order. And similarly, I'll take the I component, cross its row and column. So we're talking about 8 plus 8, that's 16. If we look for the j component, it's always negative because of that. Cross its row and column, so that's 12 plus 2, that is 14. And to find the k component, that's 24 minus 4, which is 20. There, that simple. And if I'd like to take w cross with w, again, I, j, k, w is 2, 6, 7, 2, 6, 7. So if I cross i's row and column, I'm talking about 42 minus 42. If I take j's, 14 minus 14, and k, and you'll figure that out quickly, any vector crossed with itself is 0. Next on the list, let u, v, and w be the vectors in exercise 1 and 2. Okay, use Lagrange identity to rewrite the expression using only dot products and scalar multiples, and then confirm your result by evaluating both sides of the identity. Well, if you recall, that is the magnitude of v. Again, you're not responsible to memorize that. I wouldn't ask you to do it the way they're mentioning that. I would actually write it and say verify it. There, that's Lagrange. That's Lagrange identity. So let's see how that works. Well, I could do this a few different ways. First, let's find the cross product. If I take v crossed with u, that is I, j, k. List v first. V was 3, 2, -1. And list u after. U was, oh, I put them backwards, didn't I? List v first, then u, 0, 2, 3. Now, does it matter which one comes first? Yes, it does. If you switch those, you get a negative. Let's see. So they want v first, 0 to -3, 3 to -1. Okay. So the cross product of those, the I component will be cross its row and column. That is -2 minus -2 plus 6. That's 4. The j is always negative. Cross j's row and column. That's 0 minus a -9, so that's 9. And the k component, you'll get 0 minus 6. There you go. So if we do the magnitude of that, that's the square root of 16 plus 81 plus 36. And what would that be? That would be the square root of 80, 90, 120, 133. And if you square that, that's simply 133. Now, the magnitude of v, well, we just figured out that v is this. That's the square root of 0 plus 4 plus 9. multiplied by the magnitude of u. There is u. That is the square root of 9 plus 4 plus 1. Of course, we're squaring that. And we're squaring this. Minus the dot of the 2. If we take the dot of the 2, that's 0. Plus 4 plus 3. So 133 should equal. That is 4 plus 9, 13. The square and the square root cancel out. That is 14 minus 7. And 13 times, of course, you could use a calculator for that. That's 12, 3, 4, 4, 1, 2. That's not working. Let me double check my math really quick. I found a mistake. You have to square that. So that is what? 182 minus 49. If you take 49 away, 9 out of 12 is a 3. That becomes a 7. 4 out of 7 is a 3 and a 1. So 133 equals 133. This is just nothing more than practice of verifying certain identities. Well, let's see. Use the cross product to find a vector that's orthogonal to both of those. Well, that's simple. The vector that's orthogonal to both of those is the cross product of both. That will be orthogonal to both. 1, 1, negative 2, 2, negative 1, 2. The I component across this row and column. You're talking about the determinant of this, which is 2 minus 2, that's 0. If I go for the j component across this row and that column, that is 2 plus 2, that is 4. And if I go for the j component, that is a negative 1 minus 2, that's negative 3. So there it is, 0, negative 4, negative 3. This is a vector that's orthogonal to both of those. You could, of course, multiply them if you wish. Let me make sure I didn't make a mistake. And let's see. That was negative 2 minus 2, that's right. The j component would be 2. Oh, that would be negative 2 minus 4. That's negative 6. My mistake. Right? If I want to find the j component, I messed up. That is negative 2 minus a negative 4, which is negative 2. One second, let me double check. I was just lost it. So I'm looking at 1, 2, negative 2. Why am I having to get that? Is 2 minus a negative 4. Yeah, there you go. That's a 6. Correct. And it's negative because it's a j component. All right, so that works. And you could check your work. Dot u times the cross, you'll get 0. Take v, dot it with the cross, you'll get a 0 as well. Number 10, the same deal, another practice, but here we're asked for something slightly different. Find the area of the parallelogram. Remember, if I take vector u, cross it with vector v, I'll get this vector, perpendicular to both. And the magnitude of this would be the area of the parallelogram. If I want to find the area of the triangle, I just take half of that. So I need to find first u cross v. How did that happen? I, j, k, 3, negative 1, 4, 6, negative 2, 8. So the I component, if I cross its row and column, I'll be left with those. That's negative 8 minus 8, minus a negative 8 plus 8. That's 0. And if I take the j component, I'll get 24 minus 20. That's 0. That's odd. This is 0. And if I take the k component, that's negative 6 plus. Are those multiples of each other? 3 times 2. Yeah, okay, they're multiples of each other. So this is 0, 0, 0. So, you know, if they're multiple of each other, then the magnitude of this is U cross V, would be the magnitude of this. Of course, that's 0 in this case. Not very interesting. Find the area of the triangle by the following 3. Well, guess what? Every time you want to do this, the catch, you want the two vectors to share a common vertex. So if this is the triangle in 3 dimensions, I'll take AB, call that A. Well, that is end minus beginning. 2 minus 1 is 1, and 2 minus 1 is 1. And I'll take AC, call that B. AC would be 3 minus 1 is 2. Negative 3 minus 1 is negative 4. Okay. And now, if I want to find the cross product of those, well, I have to write them in 3 dimensions. That is I, J, K. So that's 1, 1, 0, and 2, negative 4, 0. That would be 0. And the J component is 0. But the K component is negative 4 minus 2. That will be a negative 6. Let me make sure. 2, 1, that's right. 2 and negative 4. And so this is A cross B. Okay. Now if I find the magnitude of this, that's the square root of 0 plus 0 plus 0 plus 36, which is 6. But remember, they want the area of the triangle, so that will be half of this. The area of the triangle will be 3 units, square units. All right. How about if they made it 3D? Well, that's the same as we just did. Find PQ. Again, the key is they must share the same vertex. So PQ is end minus beginning 0 minus 1, that's negative 1. 3 plus 1 is 4, and 4 minus 2 is 2. And if I take B to be the vector PR, that's the crucial part. You could do this, you could start QRQP if you want, or RQRP in any order. So if I take those two, 6 minus 1 is 5, 1 plus 1 is 2, and 8 minus 2 is 6. Take the cross product of those. So A cross B would be, the I component would be 24 minus 4, that's 20. The J component would be a negative 6 minus 10, negative 16. And the K component would be negative 2 minus 20, negative 22. They want the area of the triangle. So area of the triangle will be 1/2 the magnitude of this. And the magnitude is the square root of 400 plus 16 squared. I believe that's 256, if I'm not mistaken. Plus negative 22 squared. I don't know what that is. Negative 22 squared. Let me plug that in my calculator really quick. That turns out to be the square root of 285. Again, you could use a calculator to figure these out. No need to do all of this by hand. Okay. Determine if U, V, and W lie in the same plane when positioned so that their initial points coincide. Okay, that's the theorem we're talking about, this theorem. You could take U dot V cross W and see if you get a 0, or you could write it that way. It's up to you. So you could say U dot it with V cross W. You could find V cross W. So let's see. V cross W would be, you could list them under here. You could list 1, negative 1, 0. and you could do the determinant of that. So you could say that is, so the cross product V cross W will be 0 minus a negative 1 is 1. The J component will be negative 0 minus 1, so that's a plus 1. And the K component would be a negative 4 plus negative 4 plus 1 is 5 there. And you could say, well, let's see, what is U dot that? That will be 5, negative 2, 1. Dot it with 1, 1, 5, and let's see what we get. We get a 5 minus 2 plus 5. We'll get a well, that must be a typo. Let me double check really quick. Yeah, I found a mistake. It's just right there. When I do that J, that is negative 4 plus 1. That's a negative 3. There it is. So if I dot those, that will be a negative 3. That will be 0. So yes. Or you could use the theorem by saying, if you want U dotted with V cross W, you could simply list U first, V after that, and again, whatever makes you happy. So remember, you could pick any row or column. If I always want to stick with this, I'm going to take 5 times cross its row and column. So negative 1 plus 1, that's a 0, minus a negative 2 cross its row and column, that's 4 minus 1, plus 1 cross its row and column, that will be a negative 4 plus 1, which is negative 3, that will be 0, that will be a positive 2 times 3, that is 6. Oh boy, okay, what's going on? You know, I'm rushing, I don't know, I'm rushing, let me slow down a bit. So if I take, here they are, let me make sure, 4, negative 1, 1, and 1, negative 1, 0. So let's make sure that's how this works out. Okay, if I take the first, that's a 5, and let me write them out, cross its row and column, negative 1, 1, negative 1, 0, minus a negative 2 is plus 2, cross the middle row and column, 4, 1, 1, 0, and 1, cross the last row and column, that's 4, negative 1, 1, negative 1, so that's 5 into 0 plus 1, that's 1, plus 2 into 0 minus 1, plus 1 into negative 4, plus 1 is negative 3, so that is 5 minus 2 minus 3, that is a 0. Notice we get the same thing. So either way will work, it doesn't matter. You don't have to really memorize that. You could just do that work yourself. Remember, this can be a scalar. And that's pretty much it for this section. That was going to add the torque problem, number 31, but there's only one problem, one on work, one on torque, but that's pretty good. There it is.